Okay, 5.3c, College Algebra, Matrices and Systems of Equations. We're in the middle of page 465, dealing with matrices, and I just got through in the last video the first three rows, and that is to get in row echelon form, and I talked about those three rules. And if a fourth property is satisfied, if you have like a whole bunch of columns, and each column that has a 1 and everywhere else there are zeros, it is considered a reduced row echelon form. So let's look at example 2 and just be able to determine whether these 6 matrices are in row echelon form, and if any of them are in row echelon or reduced row echelon form. Alright, let's look at A. A is in row echelon form. The ones, as you go down to the next rows, are to the right of the previous one. The first non-zero element is a 1. So in the first row, obviously there is a 1 there. The second row, you have a 0 and then a 1, but the one to the left of the 1 is a 0, so that works. And in the third row, there's 2 zeros to the left of the 1, and that works too. As long as the numbers to the left of a 1 are zeros, you're okay. All the rows consisting of zeros are at the bottom of the matrix. Well, there aren't any that are just zeros, so that doesn't even count. And if a fourth property, a matrix, okay, each column that contains a leading one has zeros everywhere else. Okay, so it's not reduced. We look at B. First non-zero elements are not ones. So that one is neither. We get to C. Second row there has a 3, doesn't have a 1, so that's not in row echelon form. We look at D. Okay, that is row echelon form. E is row echelon form. And F. F is got all zeros in that second row, but it's not at the bottom, so that's not in row echelon form. If you look at D and E, not only are the row echelon criteria met, but each column that contains a leading 1 also has zeros everywhere else. Okay, we don't care about the right-hand side of that vertical line. We're just looking at the coefficient matrix there. And it's all 1s and all zeros, so it is in reduced row echelon form. So here is the answer that we came up with in example 1. And again, if we were to write this in system of equation form or equation form, we'd get this. Okay, so z equals negative 1/2. I explained this earlier. We take this negative 1/2, put it here, find the y. Take the negative 1/2 here. Whatever value we found for y here goes here, and we can solve for x. Okay, so we find x, y, and z. That's my preferred way of doing it. The book goes into another step, which is called the Gaussian-Jordan elimination method. And what that does is it changes these 3 numbers here to zeros as well. And when we change these 3 numbers to zeros, it would be x equals this, y equals this, z equals this. So you don't have to back substitute in, which I prefer doing personally, but we do need to continue on with this. And really all we're doing is the same thing we did to get these to be zeros, but now we're going to continue on and make these 3 the zeros. Okay, so that's the only difference, is you not only make everything to the left of the main diagonal zeros, but everything to the right of the main diagonal zeros. and that is called Gaussian Jordan elimination in order to do that. Okay, so we've got this one here, so let's just continue on to make these 3 zeros and see what happens. So what we're going to do is let's get rid of this -10 here. Let's turn that into a 0. Well, I look down this row or column and say, oh, well, there's a 1 here. So if I multiply this entire thing by 10, this will give me 10 here. Added to that will give me a 0. So again, this row won't change, but when I add the changed row to this row will change. And so that's what I want to do. Okay, and one of the reasons I like it is because it'll change that to a 0. It won't change this at all because that's a 0 there. So 10 times 0 is 0 plus -2. That'll stay a -2. 10 times 0 is 0 plus 1. That'll stay a 1. So it's nice because it's only going to change what we want here. Okay, so let's go ahead and, like I did before, write the one we're going to multiply by 10. We're going to leave it the same. We're going to leave the middle row the same because we're not doing anything with that. And we're going to change the top row. So 10 times 0 is 0 plus 1 is 1. 10 times 0 is 0 plus -2. 10 times 1 is 10 plus -10. 10 times -1/2 is -5 plus -6. Okay? So there we have a new row there with that -10 turning into a 0. Okay, now we want this to be a 0. And see, there's a 1 underneath it, so we can so that's why we're going to make that into a 0. We could make this into a 0 because there's a 1 underneath it, but let's do this one first. So we're going to multiply my third row by a -8. And then I'm going to add it to the second row to get that to change. So again, my third row doesn't change, and my first row doesn't change. Okay, and my third row doesn't change. So my second row will change. Okay, so -8 times 0 is 0 plus 0. So that will be a 0. -8 times 0 plus 1, that won't change. -8 times 1 is -8 plus 8, so it makes that a 0. And -8 times -1/2 is 4 plus 3. That'll make that a 7. So hopefully you're kind of getting the hang of what's going on here. I have a -2 that needs to change to a 0, so I look with a row that has a 1 by it. And since this one has a 1, I'm going to multiply this entire thing by a +2. And let's go ahead and write what's going on here. So this middle row won't change. And my bottom row won't change. Just my top row will change. So 2 times 0 is 0 plus 1. That'll stay a 1. 2 times 1 is 1 plus that will change to a 0. 2 times 0 is 0 plus 0. That'll stay a 0. And 2 times 7 is 14 plus 11 gives me a +3. 3. Come on, give me a 3. Alright, so now I've changed all of my rows. So x equals 3, y equals 7, z equals -1/2. So that saved me from having to back substitute. So see, I found z is -1/2 here, and then I put it in here. I don't have to do that here. I'm given all of my answers here because these are all ones, x, y, and z, and I'm done. So in the homework, it gives you a choice of whether you use just the Gaussian way or the Gauss-Jordan elimination method. So either one you want to do is fine. So that's it for that one. Let's look at example 4. So this is example 4. There's it written in the system. There it's written in the augmented matrix. And as you do this, whether you use the Gaussian elimination method or the Gauss-Jordan elimination method, what you're going to do is sometimes you're going to have some weird things happen. In this particular one, when you solve it using either one of those methods, this is going to turn into all zeros. This row here is going to turn into all zeros. When that happens, when you get a row that consists only of zeros, basically what that means is you have an infinite number of answers here. That means that the graph lies on each other and there's an infinite number of solutions. When you get this bottom row to be all zeros, or any row to be all zeros, and this number over here is a non-zero number, that means you get 0 equals some number. So say it's a 13. If this is a 0, this is a 0, this is a 0, equals 13. This is a non-true statement, so therefore there is no answer. There is no solution to this, so you give me that. Alright, so that's pretty much what example 4 does, is it gives you a couple different options there of what you're going to get for an answer. And that should be enough to get you started on lessons 5.3.